And his collaborator, Jay Shim, will also join us for some answers. So please type your questions in the comment area at the right side of the screen in the YouTube channel. And the questions you're raising up now and the questions that you have previously asked through the form are going to be answered at the end of this webinar. So I'll hand over the mic to Steve, and I hope you enjoy the webinar.
Okay, thank you, Rodrigo, for that introduction. Hello, everyone. So as Rodrigo mentioned, my name is Steve Maas, and I am a software developer on the FEBio project, which is a nonlinear finite element solver for biomechanics.
I'm going to be answered at the end of this webinar. So
I hear somebody else's voice. Okay, so what I thought I'd do today is start with an overview of the FEBio project, mostly targeted to those who are not familiar with it yet. Then we'll go over some examples of new capabilities in FEBio. We'll follow that with a demo/tutorial of FEBio Studio, which is our newest development environment for creating, running, and analyzing FEBio models. And then we should have about 10 to 15 minutes left at the end for a Q&A session. So let's get started with the overview of the FEBio project. So the finite element method, which is a numerical method for solving the equations of physics, has been around for a very long time and has been used in many areas of engineering, including computational biomechanics. Now, when we started FEBio, which was around 2005, we and many people in our field had to rely on finite element software that was traditionally, or that was designed for the traditional engineering mechanics applications. And although these softwares are great at what they do, for the particular application of biomechanics, we and many other researchers felt that they have limitations. They often lacked key simulation capabilities or relevant constitutive models. They were often commercial, which means closed source, making them difficult to verify and see exactly how they are doing things. They didn't always have good support or good documentation, and as a result, researchers were often forced to develop their own finite element codes. And so we were kind of in the same boat, but instead of just developing another in-house FE code, we wanted to create a software package that would try to address some of these limitations. So that led to the start of the FEBio project. As I mentioned, this was around 2005 when I joined Dr. Weiss's lab at the University of Utah. 2006, Dr. Ateshian joined us, so he was already collaborating with Dr. Weiss. I had a very strong interest in modeling of computational biomechanics, especially in areas like biphasic and multiphasic modeling. Then in 2007, we released our first version, although we didn't get funded until 2009. Since then, we've been fairly fortunate that the NIH has continued to fund us financially, for which we are, of course, very grateful. We had our first grant renewal in 2012. One big aim of that grant was the implementation of a plugins framework that allowed users to create new features without having to modify the source code. We had our second grant renewal in 2016. A big aim of that grant was the implementation of a fluid and FSI solver, which was released in 2018. Then in 2019, we made a big step forward by switching from our custom license to a truly open source license. And then brings us to today, where we'll talk a bit about FEBio. Over the years, of course, we've added a lot of features to FEBio, more than I can sum right now. But I just want to mention a few important things. So first of all, FEBio is a multi-physics code in the true sense of the word. We can not only do nonlinear solid mechanics, but we can couple that with different types of physics, which allows us to simulate multi-physics mixtures. When we couple it with our fluid mechanics solvers, we can do FSI, we could do chemical reactions. We could also do heat conduction, but at this point that is still a separate module. And a little bit more on the multi-physics, something that truly sets us apart from other finite element codes. So we have a lot of capability for modeling complex mixtures. May include any number of solutes. They can be neutral, they can be charged, they can interact through chemical reactions and so forth. Another thing that sets us apart is that we have a very large library of constitutive models that were specifically designed for applications in biomechanics and biophysics. So we have different kinds of hyperelastic materials with different types of symmetries. We can model fibers individually or as distributions, damage, fatigue, pre-strain, active contraction for modeling muscular tissues. And you can combine many of these materials together to create your own custom materials. And I'm not talking about the plugin framework here, I'm just talking about the way you would define materials in FEBio. Of course, we have all the boundary conditions and loading conditions you would expect from a finite element code, but in addition, we also have some advanced contact formulations that allow you to simulate things like fluid and mass transport going across the contact interface. We also support rigid body mechanics, so you can couple deformable mechanics with rigid body mechanics in a single simulation. And then, as I mentioned, we also support a plugin framework. Now, of course, having a lot of features is great, but the big question, of course, is FEBio being used by the community? So over the years, we tried to collect some statistics that help us answer that question. And so right now, we're looking at over 100,000 downloads of FEBio and its supporting software. We have about 12,000 users on FEBio.org, which is our main website, about 1,300 users. We have over 500 publications that we are aware of, where people have used FEBio in their research. And we don't have an exact statistic on this, but we know that many people are using FEBio as a teaching tool in graduate courses all over the world. As far as areas of application where FEBio is being used, we know that it's being used in musculoskeletal mechanics, soft tissue mechanics, cell mechanics. I won't read the entire list. I guess the take-home message here is that FEBio is being used by the community and in the research, and I think it's having an impact as well. So if you haven't used FEBio, I hope this convinces you to at least take a closer look and maybe give it a try. So let's look at some examples of some relatively new features. So the fluid solver has been out for a couple of years, but it still remains a very active area of development and research for us. So I still include it as a relatively new feature. So what we're seeing here is a simulation of a bifurcated artery. This was a verification problem that we used to compare FEBio's performance to SimVascular and ANSYS. The next example shows that same artery, but in an FSI simulation. Now, this is not perhaps the most physically realistic simulation, but it kind of gives you a scope of the deformations that we can handle with our FSI solver. So this shows a more physically realistic simulation. The deformation is not as pronounced, but you can still see the walls deform. So in this case, we modeled the surrounding tissue and used more realistic constitutive models for the solid and for the fluid. So then let's talk a bit about some new capabilities of FEBio 3. So one thing we really tried to expand on in FEBio 3 was the ability to introduce heterogeneity in your models. You could kind of do that with previous version of FEBio as well, but it usually required developing a plugin. So now we've added various mechanisms for making model parameters heterogeneous without going through the plugin framework. And one of the most powerful tools that were added was support for mathematical expressions. So you can use mathematical expressions to define material parameters, fiber orientation, boundary conditions, and loads. And you can even define an entire constitutive model by giving the mathematical expression of the strain energy function. So no need to do any tedious derivations for stress and tangents. FEBio can now do all that stuff for you. We also implement a framework for doing adaptive mesh refinement. We have both template-based refinement strategies as well as whole mesh refinement strategies. And one of the neat aspects of this framework is that it ties in seamlessly with the plugin framework, so users have complete control over when and where they want to do the adaptive mesh refinement. Related to that is mesh erosion. This is also a way to adapt your mesh, but in this case you're just turning off elements. And again, it ties into the plugin framework, so users can decide when and where to turn off elements, and that allows you to simulate things like tearing or projectiles going through tissues. We also implemented an arc-linked solver, which is useful for getting through some difficult buckling or instabilities that might be difficult to solve with our traditional Newton-based approaches. And then we also added several iterative linear solvers. They promise to speed up computations quite significantly. Now, the only caveat with that is that they are more sensitive to the application domain. So this is why we have multiple iterative solvers that we implemented, because you might have to try a few to find one that works for your particular application. But if it does work, you might be able to speed up your computations quite a bit. Another new thing that we'll be supporting with FEBio 3 are FEBio apps. So these are small user-created user interfaces that can control one or multiple FEBio models. And you can even control these models interactively, which means you can change parameters as models are running through the user interface. And we think this is going to be very useful for doing demos at conferences or as a teaching tool. So that brings us to FEBio Studio, which, as I mentioned, is our newest integrated environment for creating, running, and analyzing FEBio models. So if you're familiar with PreView, if you're familiar with FEBio already, then you're probably using PreView on the pre-processing side, and then our PostView on the post-processing side. So what we did is we brought these two together. But FEBio Studio is more than just a sum of those two. So with FEBio Studio, we're also trying to expand our modeling capabilities and our mesh generation algorithms. FEBio Studio will also come pre-packaged with the latest version of FEBio, so you don't need to install that separately anymore. FEBio Studio will also have much better support for adding image data in your simulation pipeline. And also one of the exciting new features is that it will provide access to a model repository where users can download and share models with the community. So that brings us to the demo part of the webinar. So I'm going to be switching screens here. So first of all, I want to mention that all the files that I'll be showing here will be made available after the webinar. The version of FEBio Studio that I'm using here was uploaded to our website on Friday. So if you download the version FEBio Studio from our website since Friday, you will have the version that I'm showing here. Okay, so let's get started. When FEBio starts, you will see the project manager screen. So the main purpose of this screen is so you can kind of select an application that you're going to be working on, and this is going to be used to populate certain menu and dialog boxes to basically only show you relevant features. Now, in this case, I'm going to start from something I already prepared a little bit. So what we're looking at here is a model of a pelvic cartilage that includes the labrum. And in this demo, what I'm going to do is I'm going to load an implant into this model and use that implant to apply pressure onto the cartilage to deform it, and then we can look at the stresses and strain that are generated. So I will talk about all the different UI components as we come across them. So the first thing we'll have to do is import the geometry. So the first thing I'm going to import is a model of the pelvis. So these are all the different file formats that we are currently supporting. The pelvis in this case is a surf file, which essentially is a triangulated surface mesh, as you can see. And then the next thing, what we need to import is the implant. So the implant is a step file, which is a CAD file. So we support right now step and BREP files. So let's go ahead and import that as well. There you go. So now we have all the geometry that defines our model. The next thing we have to do is create meshes for these models. So to create meshes, we would have to go to the Build panel here. The Build panel has a few different tabs that can be used for creating and editing and meshing geometry. So let's start with the implant. Now the implant is going to be a rigid body, so it doesn't matter too much what the mesh looks like. So we're going to start with a very coarse mesh. Okay, this is the biggest part. Will take a few seconds. The other parts will go much quicker. So now we have a mesh for that part. We'll have to do the same for this part. Okay, now the last part here, this part is going to go into contact with the cartilage. So I want to create a mesh that is a little bit finer because I want to be able to capture that geometry of that spherical surface accurately. So we're going to use a moderate mesh, and we're going to use quadratic tetrahedral elements so that we can capture that curvature quite well. Okay, this should be done any second. There we go. Okay, so now we have the geometry, we have the mesh. Let's think about the physics. So what I'm going to do is I'm going to first move this implant up into the cartilage until it makes contact. The way I'm going to do that is by simply prescribing the displacement of that implant. Then I'm going to switch from a displacement control to a force control because usually what people are interested in is applying a force to this implant, not a particular displacement. And then I'm also going to add a rotation to the implant as well. So let's get started on that. So if we go now to our model panel, we will see a model tree here, which lists all the items in our model. So you can see here all the geometry, and when you see a little triangle like that, that means that there is an issue with this component. And in this case, it says the object is not meshed. So the object that I'm referring to here is the pelvis. Now, although we imported a mesh, it was just a surface mesh. And so FEBio Studio does not consider that mesh useful for finite element modeling. Usually what you would do when you import a surface mesh is you use that to generate a volumetric mesh. Right? So we'll have to go back to our build panel on the mesh tab. And so we can create our volumetric mesh here. But because this is just going to be a rigid body, we're just going to basically use that same surface, just convert it to a shell mesh with 0 thickness. Okay, now if we go back to the model panel, we see that the triangle is gone. So we can move on to the next part. So let's think about some materials. So to add a material, you right-click on this item, you select Add Material. In this case, we're not going for physical realism, so we're just going to pick a simple model that will run quickly, which will be the Neo-Hawking model, and that's the material we're going to assign to the cartilage. Okay, so we select the cartilage here, and then here at the bottom, there's a selection box. If you click the plus button, it will assign that material to the cartilage. Next, we'll create a rigid body for the pelvis. So the way we do that is we create a material again, just like we did before, but now we select Other category, rigid body, and we add that. So let's name that pelvis. And we'll assign that to the pelvis geometry. And then we're also going to add a rigid body for the implant. So we'll select all the components implant. And so you'll see that each material has its own color. The object that was assigned to that material will show the same color. And of the default color scheme that is being used, I don't blame you, but you can easily change that by clicking on these color boxes. So we'll just change that quickly to something a little bit more appealing. And for the implant, we'll just do a gray. And let me rename this to implant. Okay, so we've added the materials, but we're not quite done yet. So because these are rigid bodies, we have to think about the rigid body degrees of freedom. In particular, the center of mass or the center of rotation. For the pelvis, which is going to be completely fixed, it doesn't really matter. But for the implant, we are going to rotate this implant around the center of mass of the top part. So FEBio can calculate the center of mass automatically, and that's usually what you want to do in a dynamic simulation, for example, but in a static simulation, it's often more convenient to specify that center of rotation. So how do we find the center of rotation of this spherical part here? So we can kind of look at these values here. So they're kind of they're the center of this box here, which is probably a good enough approximation, but we can do a little bit better. So let's go ahead and hide some of this so we get a better view of the implant. And to hide a geometry, you just click it and then push the H shortcut key. So we'll hide everything until we have the implant. And what we'll do now is we'll fit a sphere to this top part. So the way we do that is we go back to our build panel. There is a tools tab. Make sure it's selected. There's a sphere fit tool. And then you click on fit and it will tell you the coordinates and the radius of that sphere. So let's say it is about 31, 197, 0. So we'll enter that as our center of mass coordinates for the implant. Okay, so now you can kind of see that there is this diamond-shaped icon now at the center of our rotation. Okay, so now we're done with setting up the materials. So let's talk about boundary conditions. Now in this case, because all the kinematics is prescribed through rigid bodies, we actually don't need boundary conditions. Instead, we're going to use rigid constraints. So let me first show all the geometry again. The first constraint we're going to add is for the pelvis. Since the pelvis is not going to move, we just fix all 6 of the rigid body degrees of freedom. Let's call that fix pelvis. For the implant, we have to prescribe a displacement, a force, and a rotation. But let's first add a fixed rigid displacement for all the degrees that we're not going to be using. So we won't use the x displacement or z displacement, and these rotations. Let's call that fix implant. Okay. All right, the first prescribed displacement that we're going to add for the implant is the y displacement. So in this case, you can see here that the y direction is pointing up into the pelvis. So that's how we know that we want to displace in the y direction. We'll choose a value of 0.5. Now, before I continue with that, let's add an analysis step here. So the analysis step will tell FEBio what we're going to do. In this case, we're just going to add a structural mechanics step. Now, we're going to be using all the default parameters, but I want to draw your attention to these time steppings. So by default, a step has 10 times step. Each step size is 0.1. So in FEBio, the simulation is going to run from time 0 to time 1 in 10 different time steps. Now, what does that mean for our displacements? So what FEBio Studio actually does is it attaches what we call a load curve to this parameter. And this load curve is going to be multiplied by this value when FEBio goes through these different time steps. So you can look at these load curves by going through the curve editor here. You'll see another model tree where you can now go down to the value of your prescribed displacement. And you'll see that by default, FEBio Studio assigned a linear ramp from 0 to 1. Right? So this means that when we run FEBio, the displacement will go from value 0 to value 0.5 in linear increments. So let's rename that y displacement so we won't get confused later. Okay, so we've done the displacement. Let's now add the rotation. So we go back, add rigid constraint, select implant, prescribe rotation. In this case, we choose the X rotation and we'll pin in a value of 0.4. So again, we can go back to the curve editor and look at the value that was assigned, or the load curve that was assigned, so we get the same linear ramp. Now in this case, I don't want the rotation to start until the second step, which reminds me, let's add a second step. Okay, the second step will go from time 1 to time 2. So we can edit this curve by just dragging these nodes. And so now the rotation will happen only during the second step. Okay, so again, let's give that a more useful name. Now we have to do one more thing. We have to switch from displacement to force control in the second step. So the way we do that is first we will add the force. So the force will be in the y direction. The value will be 873. We'll call that y force. Now you can see here that where it says step, it lists all the steps that are available, and by default it is assigned to the initial step, which basically means that this force will be applied when simulations start and will remain active during the entire simulation. So we don't want that in this case. In this case, we want this force only to be active in step 2. Then we also have to change the y displacement because we only want that displacement to be active in the first step. Okay, so how do I know which boundary conditions or constraint are part of which step? So I can open the step item here and I can see which ones are listed. So in step 1 we have the y displacement, and in step 2 we have the y force. So everything looks good. Okay, so we have one more thing to do. We have to define the contact. There are two contact interfaces that we have to add. The first contact interface we will add will tie the back of our cartilage to the pelvis. So to add a contact interface, you go to Physics, Add Contact, and since our pelvis is a rigid body, we're just going to use a rigid interface. We have to select the material that this interface will attach to, which is the pelvis in this case, and then we have to select the surface to which this rigid interface will be applied. So that surface is the back of the cartilage, which is difficult to see. So I'm going to show you a couple ways how you can actually get to that surface. So of course you can hide the pelvis, and that will give you access to the surface, or you can actually just select the pelvis. It will become transparent, and now you can select through the pelvis to get to that back surface. So let's add that to our contact. Okay, so the second interface is a sliding interface, a frictionless sliding interface between the front of the cartilage and the top of the implant. So to do that, we go back to Physics, Add Contact. In this case, we choose Sliding Elastic. So we have to define the two surfaces. So for the primary surface, we will pick the inside of the cartilage. And then for the secondary surface, we will pick the implant. Okay, so that completes setting up all the physics of the model. So we are now ready to run this model in FEBio. To do that, you just click on the little FEBio icon that you see here. This brings up the Run FEBio dialog. So one of the nice things about this is that you can set your launch configurations. If you have multiple versions of FEBio installed, you will be able to choose here which version you can use. But more importantly, you can add your own custom configurations. So let's just add a test one here. And you can even set up remote launch configurations, which will run FEBio on a remote server. So you would enter the server address here, your username, the location of where you want this model to run. And then when you run this model through FEBio Studio, it will actually call FEBio on the server. And then after the model is completed, we'll pull back all the files so you can continue working in FEBio Studio. Now in this case, we'll just stick with our local launch configuration and start running. So FEBio is now running in the background, and it will provide some output to the screen so you can kind of see what's going on. So if you're new to FEBio, then these numbers may not mean much to you, but basically it's going through the time steps, and what it's supposed to be printing is some convergence information. So we probably forgot something, which is why it's all zeros, but no problem. We can just stop it here. Never happened, and continue working here on this model. This is the complete model that we set up, but I already ran this model the computer, so we can just go ahead and open that plot file and take a look at the results here. So we have two time steps here, or two analysis steps, each about 10 time steps. So we have 22 steps here, and we can start by just doing a quick little animation of this. So you see that the implant is going up into the cartilage, and then in the second step, we apply that rotation. So let's take a look at, for instance, the stress in the cartilage. Now, this implant is kind of in the way, so let me first show you a couple ways how we can kind of look into the cartilage. The easiest way is simply hiding the implant. Now you can see the inside of the cartilage, but instead of hiding it, we can also make it transparent, so we can kind of see through it. But for now, let's just hide it. So at the top here in this drop-down dialog box, you will see all the fields that were calculated by FEBio Studio and stored in the output file. So let's take a look, for instance, at the effective stress. So now if we go through the animation, we can kind of see where the stress is building up. And as the implant is rotating, you kind of see that the stress is moving more towards the labrum. So in this, now it might be useful to kind of show the implant as well as a transparent material, so you can kind of see how the implant is moving in relation to that stress. Another way of looking through the material without having to hide or even make the implant transparent is by adding a plane cut. So the plane cut will cut the material or cut the model at a particular orientation and offset. So we can change the normal of that plane as well as the offset to kind of find a good orientation. So let's find an orientation where we can see some stress. There we go. Let's turn off the plane. And so now you can kind of see what's going on here. You see that the cartilage was compressed. We can turn on the mesh. And then as the implant rotates, the stress kind of shifts toward the labrum side of the model. Okay, so what if we want to look at particular values at particular elements or nodes? So let's turn off this plane cut and let's hide the implant again. So we can select individual elements. Let's select a few of them. And then by going to Post, New Graph, we can create a graph as a function of time for, let's say, the effective stress for the different elements that we have chosen. So while I'm on here, I want to also show a couple tools. So each of these graph windows has some tools. So there's some curve fitting capabilities. You can fit linear, quadratic, or exponential curves. And you can even type in your own mathematical equations. And it will be overlaid onto the image. You can also copy this data. You can either save it to a file or just put it on the clipboard, which allows you to paste it directly into Excel. And you can even dock these things at the bottom if you like. You can have multiple of these windows open simultaneously. So there's a lot of ways you can look at your data through these graph windows. So speaking of data, so the data panel here lists all the fields that are in your simulation right now. And in FEBio Studio, you can also add some additional fields that were not part of your analysis, but that FEBio Studio can calculate based on the data that is in the model. So you can add things like, for instance, volume ratio, which is helpful, which is useful when you're doing incompressible materials. You want to see what the volume ratio is. Let's deactivate the pelvis and the implants so we only get the data for the cartilage. And so you kind of see that we have some compression in the model here, which of course is not surprising since we used a compressible neo-Hokian material for the cartilage. You can also export this data to a file, to a text file, which allows you to import the data then in MATLAB or Excel or anywhere else where you want to do some additional post-processing of the data. So you can add additional plot fields like vector plots or tensor plots, isosurface plots, slice plots. For flow simulations, you can also add stream plots, particle flow plots. You can also do a volumetric rendering of the flow as well. And then the last thing I want to show here is that you can also take pictures and recordings of your model. So to take a picture, you would activate the capture frame here. If you double click on that border, you can choose the resolution of your image. You can move these things around to kind of compose your image here. And then when you're ready, you can take a picture in different image formats. Then, excuse me, you can also do a recording by going record, new, and select your video format. If you select an image format, it will just store each frame of the video in a separate file. So you can do an MPEG video, for example, and I won't do it here. I'll just show you a movie that I made earlier that kind of show what the capabilities are of this recording feature. So we do forward, we do the motion backwards. We can zoom in then, remove the implant, look at the stress field. And now we can zoom back out. I'll let it run one more time. We're zooming in. There's the stress field again. Okay, so that concludes the demo. But before I give the screen back to Rodrigo, I just want to say a few more things. So where can you find all this? Well, the main place to be is febio.org. This is our main website. And when you go to this website, you will have access to all our downloads. You can find you can find the knowledge base there as well, where you can locate all our manuals and tutorials. There will also be a link to the FEBio forum where you can ask questions to the community and to the developers as well, because we are monitoring that forum as well, and we're always happy to answer any questions you may have there. You can also post bug reports there, as well as make features requests. And then finally, I want to say thank you on behalf of the entire FEBio team. Thank you to the European Society of Biomechanics, and then in particular to Essen, Rodrigo, and Enrico for giving us the opportunity to present FEBio through their webinar series. And then I want to thank you, whoever is watching. I hope that you found the webinar informative and helpful. And then at this point, I welcome any questions that you may have. Thanks.
All right. So thanks a lot, Steve. That was a great presentation.
Thank you.
And actually, we had an online question and answer going on between our watchers and Jeff Weiss that was answering some questions. So I am not going to repeat those that were answered live by Jeff. So we also thank him. But we'll move on with other questions that we have from our audience. So a few people was concerned on the material properties. So we had a few questions whether we can define material properties based on CT data, or whether you create, let's say, custom materials in FEBio.
So about the custom materials, so the answer is yes. So we have a feature called the solid mixtures, which allows you to combine different constitutive models to kind of make up your own constitutive model. So that is, I would say, the easiest way to create custom materials. Then through our plugin framework, you can add new constitutive models as well. And in fact, if you go to our website, there is a plugins page. In fact, let me see if I can just go there quickly. Oops. So which has some examples. If you want to do a constitutive model that is not in FEBio yet, then the best way to go is by introducing a plugin that has where you can define your own material. And so we have a couple here. This one is a material plugin, and there is also, I think, a simple example, the NeoHokin PI. This is a simple example that you can use as a standard, as a template. And then also a third way, which is a new way in FEBio 3, is if you have a strain energy function, you can simply just type that into the, excuse me, my voice is failing me. You can type that into the model in the material definition, and then FEBio will do all the calculations needed to evaluate the strains and the stress from that strain energy function. As far as the CT data is concerned, so we are working on features that allow you to import image data in FEBio Studio. In fact, we already have some capabilities to do that. And one of the next things that we are working on is being able to map that image data onto either material parameters or boundary conditions or load as well. So this is something that we'll be able to do in the very near future.
All right, great. So thanks again. All right. So we have a more multi-physics question here. It says, can we use FEBio to model heat transfer and deformation at the same time?
So, so right now our heat transfer module is a separate plugin, and it does not interact yet with with our mechanics solver. Now we have thought about adding it, but I guess right now motivation, we haven't heard a lot from the audience, from the users, that they want that. But if that changes, then this is of course something we're more than happy to look into, and probably wouldn't be too bad to implement, because of course we have all the mechanics, we have all the heat transfer, so it's just a matter of coupling the two together. So if this is something that users are interested in, let us know, and we'll be more than happy to look into that.
All right, great. So let me just double check if we had all the questions. Okay, people are saying that they have a few issues with the first few questions. So maybe we can take a second to repeat one of them, that if it's not a problem for you. So I will repeat one of the first questions. So the one dealing with the material. So can you take material models from CT or build your own, let's say, give your own properties to the material? Maybe you can show the audience again what you showed us for the NeoHokin and stuff, so that they can see it, that the video was not there.
You mean in the demo with FEBio Studio?
No, when I ask you about whether you can plug in your own material model, you showed us from the FEBio website how to do that. And also,
okay, sure.
if we can repeat the question of FSI from Jay, that the audience says that they couldn't see that one.
Okay, sure. So about custom material models, so I guess when people use when people say custom material models, there are two ways we can interpret this. Either they're talking about their own constitutive model, or they want to customize material properties through CT data. So the first part, creating your own constitutive models, so that is possible, but you'll have to use the plugin framework. So you can use the plugin framework to create your own custom material implementations. And then what I showed was here on the FEBio.org website, there is a plugins tab, which takes you to all the plugins that we currently have in FEBio. And there are a couple. There's the one Shinoi material, and there's also at the very bottom the Neo-Hookian plugin material. So you can use these examples as starting points for your own constitutive model implementation. So I also mentioned that in FEBio 3, you now also have the ability to type in your strain energy density function, so you don't actually have to implement a plugin. If you have a hyperelastic material and you just have the strain energy function, you can type that into the input file, and FEBio will do all the calculations for you. And then related to customizing your material parameters via CT data. And so I mentioned that this is something that in FEBio 3, as I mentioned, we have a lot of ways of making material parameters heterogeneous. And so one way that you'll be able to do that in the very near future is through image data through FEBio Studio. And then I'll hand it back to Jay for the FSI question.
Yeah, so for FSI, so it's compatible with any like hyperelastic solid model that's currently in FEBio and even a solid mixture. So you could include damage into your solid for FSI. And then what FSI does is that it makes sure that the solid domain knows what the stresses and pressures are from the fluid domain, so that's able to calculate the damage properly. So yes, it is possible in FSI to include damage into the surrounding solid.
All right, great. So with that said, I would like to close. So thanks a lot, Steve. Thanks very, very much for the time you dedicated to this one. Thanks to Jay also for the questions. I want to thank everyone at the ESB student committee for their support. Last but not least, I will want to thank our audience for being here. And as Steve just said, we will put some info below the video description so that they can make more questions or get in touch with you if you have a forum. And also, someone was asking for the files from this presentation, so that will be a way for the audience to interact further with you guys that are the real developers of this.
Okay.
Okay, thanks a lot.
Thank you so much.
See you.